Hello, and welcome to Storage System Basics for Virtualized Environments. My name is Bob Ingram. I'm a Solutions Consultant with Itachi Data Systems. The goal of this presentation is to give vSphere administrators a good working knowledge of storage systems so they can make better decisions on how to put together their storage systems for their virtualized environments. At Itachi Data Systems, we've noticed that vSphere administrators know the vSphere environments very well, but are lacking in knowledge on the storage systems. They typically rely on their storage teams within their organizations to help them with these decisions. The goal of this presentation is to give them a better working knowledge of these storage systems and how they can best utilize them in their virtualized environments. Here's the agenda for today's presentation. We'll go through current technologies, and we'll discuss Hitachi storage system solutions for the VMware environments. Media comparisons. Media, meaning disk drives. When you purchase disk drives, you would purchase capacity, but you would also purchase performance, both in IOs per second and in megabytes per second, or throughput. Typically, we would measure IOs per second in a vSphere environment because that's the most critical part. For our highest IOs per second, we'd look for solid-state disks. They're based on flash memory, and they can have very high performance. Some solid-state disks can perform over 8,000 IOs per second on a read basis and 2,000 on write, some even higher. However, this comes at a very high price. So typically a small amount of SSD will be used for critical parts of the data set. The real workhorse of the data center today is the serial attached SCSI drives. They replace the older SCSI drives, and they typically perform very well. They're available in a number of rotational speeds. 10,000 RPMs, 15,000 RPMs are typical. The nearline SAS is a relative newcomer. It's basically a SATA disk, but with a SAS interface. The SAS interface provides better reliability and better performance than the serial attached ATA. However, it has a low cost point like SATA. SATA disks are gradually being phased out of the current environments. The serial attached ATA has been the standard for high capacity, low cost storage. However, nearline SAS is replacing that very quickly. So evaluating the relative capabilities of these, we need to look at whether the performance is sequential or random. In a vSphere environment, because we have a lot of mixed I/O coming from many guest OSs to the same data store, we typically see more random IOs, where we measure IOs per second, than sequential. If we were doing a backup of a single data store, we might see sequential performance in megabytes per second, where we don't worry as much about how many IOs per second we can perform, but more about how many megabytes per second we can stream. SSD would be the highest performance, thousands to tens of thousands of IOs per second, typically limited by the bus speeds it's connected to. And it can provide 300 to 600 megabytes per second in a sequential workload. A SAS disk, depending on the rotational speed of the SAS disk, could perform a maximum of 175 to 200 IOs per second, or 150 to 200 megabytes per second. Typically, though, when planning throughput capacity, we would only use about 75 to 80% of that throughput. Nearline SAS, a little slower rotational RPM, so it would look more for 75 to 100 IOs per second, or 120 to 170 megabytes per second. SATA would give roughly the same performance. However, nearline SAS will give better capability of queuing IOs when you reach that maximum throughput. It would also give better reliability in that SAS controllers typically are more reliable than SATA controllers. And again, calculate about 70 to 80% as a maximum throughput of these, so you don't overrun the throughput of the spindles. Determining the best option. All performance questions will always start with, it depends. We need to look at the workload, the access density, and the price. There are times when multiple SAS or SATA disks can outperform SSD, especially in sequential and streaming. There are times when multiple SAS or SATA disks can outperform SSD in random, with low access density. However, when it comes to true high IOs per second, solid-state disk is the key. It will give the best for high access density and high performance. And again, your workload depends. At times, you may find that you run out of IOs per second on a disk before you run out of capacity, in which case you may not be able to use all the capacity you purchased, or you may need to move up to a higher speed media. For example, if you've purchased 4 SATA drives and you're not able to use all the capacity in those drives because you've run out of IOs per second, you may need to go with SAS drives, 10K or 15K spindles, lower capacity drives, higher performance, so you may need to go with a larger number, say 8 or 10 SAS drives, in order to have the same capacity but be able to guarantee the throughput to the applications. Typical RAID types. The typical RAID types we see used today, RAID 1, RAID 5, RAID 6, and RAID 1+0, typically called RAID 10. This chart shows a comparison of these RAID levels. We'll go into more details on the next slide. RAID 1. RAID 1 is a simple mirror disk. You have a data disk and you have a mirror of that data disk. All writes will need to be committed to both disks. Reads can come off of either disk. By adding in RAID 0 to the RAID 1 group, we add in a stripe. So RAID 10 is striped and mirrored. In the diagram here, you can see that you have data, mirror, data, mirror. And then on the next stripe, you'll have mirror and data and mirror and data. So in this example, what we're showing is 4 drives, the equivalent of 2 drives for data. So this would typically be called RAID 10 2+2. It will give better performance and better throughput than RAID 1 because we have both data and mirror on all drives. So that when we're doing reads, we can read off of all 4 drives as opposed to in RAID 1 where we can see we can only read from 1 drive. Used for very high write activity because there's no parity calculation required. It's a simple mirror. RAID 5 is using parity. RAID 5 also uses a stripe. So in the example we're showing here, which is typically called 4 data plus 1 parity, what we have is 5 drives. Notice the parity is on no one specific drive, that we write a stripe of 4 blocks of data and then calculate parity for that. Then we would write 4 blocks of data on the next 4 disks and write parity on the first disk, and etc. So by doing this, we're distributing parity, and the additional write required to write that parity is distributed amongst all the disks, rather than pushing that onto a single disk if we had a single parity disk. Also, if we're in a situation where one of these drives has failed and we need to calculate parity, we only need to calculate parity for 1 in 5 blocks as opposed to every single block. So it gives us an advantage of being able to perform better and rebuild faster than if we used a single parity disk. This gives us very good read performance because we can read from all 5 spindles at the same time, reading the data blocks off of those spindles. However, there is a slight degradation of write performance because we need to calculate parity and apply that parity to the disk. RAID 6 is getting more and more popular in the data centers for data protection. It gives a little bit more write overhead than RAID 5. However, it gives much better data protection. In this example, we're showing RAID 6 for data plus 2 parity. So we've calculated a parity P and a parity Q for every 4 blocks of striped data. In this example, any 2 disks in this group could fail, and we would still maintain our data integrity. Write overhead is slightly larger because we do need to calculate another parity block and write another parity block. However, with the increase of storage throughput and the increase of horsepower in the storage controllers, this is becoming less and less of a problem, and we're seeing a larger and larger adoption of RAID 6, especially when we get into a virtual environment where many machines may share the same data store or the same group of disks in the back end, and losing a data store would affect large number of applications. Connectivity options. There are many different connectivity options for the virtual environment. Fiber channel SAN, also called FC. It's a block device, and it presents them across a fiber channel network in fiber channel frames. It tends to be a little more costly because we need a whole separate infrastructure for fiber channel. We can't utilize our TCP IP network, but it also gives our best absolute guarantee of performance. Also our best absolute guarantee of connectivity. Network file systems. Network file system presents the files across the TCP IP network. The NFS mount would go to the ESX farm, and then the various virtual disks will be created on that NFS mount. This gives us the ability to use our existing TCP IP network without building a separate infrastructure for, say, fiber channel. But it also relies on that network and may not give quite the throughput that a fiber channel SAN can give. iSCSI. Again, iSCSI is a block type protocol. However, it's using the TCP IP network. So it's a good compromise between the additional infrastructure required for fiber channel SAN and the overhead of a networked file system. VMware supports both hardware and software iSCSI. And by that we mean hardware is an iSCSI card that we install in the ESX host. Software iSCSI is just simply a driver that uses a VM kernel network. Fiber channel over Ethernet is becoming more prevalent in the environment today. It's again a block device, but it encapsulates that block device, the fiber channel protocol, in an Ethernet frame. It allows us to use the existing TCP IP network, however with fiber channel protocol for the efficiency of fiber channel protocol. And of course there's direct attached storage, typically called DAS. This is local disks. It may be a RAID controller within the ESX host, or it may be just simply disks that are existing in the ESX host. There are still some uses for DAS, although we'll see most people are using fiber channel SAN with a lot of network file system and iSCSI. Storage tiering. We've talked about the various types of media, but how would we use them in the environment? We typically call this storage tiering. Tier 0, or the highest performance, also the highest cost, we would typically use SSD media, solid-state disk. And in Tier 1, which is a performance tier and probably the largest capacity utilized today, we typically use SAS, either 10K RPM spindles or 15K RPM spindles. But then Tier 2, we would use nearline SAS or SATA disks, which are typically 5400 or 7200 RPM spindles. These are larger capacity disks, however they don't have the throughput of SAS. So if you need extreme high performance, Tier 0, your average performance and your average cost would be on Tier 1, and if you need large capacities for, say, archival data or backup data, we would use SAS, nearline SAS, or SATA disks. Granularity of tiering. There's a number of ways we can tier. We can tier at the file level, the LUN level, or the sub-LUN or block level tiering. At the LUN level or file level, we can tier our storage based on either the LUN level, meaning the data store, or at the file level, meaning the VMDK, or the virtual disk. We could use utilities like storage vMotion in order to move the data from one location to another. And we could say we have a very critical virtual disk that's needed for, say, a high-performance SQL database. We could place that entire virtual disk on SSD by moving it to a LUN that exists on an SSD disk. However, it's not very granular. Typically in a SQL database, as we described, we may see only 20% of that data accessed over a given period of time. So we've moved the entire virtual disk from, say, Tier 2 to Tier 1 or Tier 1 to Tier 0, when the requirement is only 20% of that data is actually needed on Tier 1 or Tier 0. So that's where sub-LUN or block level tiering comes into place. What the storage system would typically do is examine the number of IOs per second or the number of IOs per hour that are happening on a particular block of data, and then determine what is the best location for that block of data and move it. So it's a very efficient use of storage. In the SQL database example, we would only move about 20% of our data to the Tier 0. We may even be able to spread that particular database across 3 tiers, and then it would dynamically move as the workload moves. So it's best to understand how your storage works. Talk to your storage vendor and understand the best way that you can utilize this tiering. So let's talk about the actual storage system architectures. Typically, a mid-range storage system would have 2 controllers. This provides redundancy in the case of a controller failure or a connectivity failure. So in this example, we have a RAID 5 group, and we have a controller 0 and a controller 1, and the host is connected to both. The RAID 5 group is connected to both. So any connectivity failure, we still have access to our data. When we get to an enterprise subsystem, and what we're looking at here is the Itachi Universal Storage Platform, we lose the concept of a controller, and now we build redundancy within the components. So if we look here on the left, we have the bed pair. Bed is an acronym for back-end director, and it is the connection to the disk drives. So by installing 2 beds, now we have connection to all these disk drives via 2 beds, and if one were to give us a problem, we would still have connectivity to our disks. Then that backend directory could be replaced live without any outage and reestablish that connectivity. Down on the bottom, we see the fed or front-end director, and that is the connectivity to the host. That could be an iSCSI fed, it could be a fiber channel fed, or it could be an NFS fed. And again, we would provide redundancy by having multiple controllers connect to the host. Same for all the components that reside within the controller architecture, the cache, the data cache. Talk to your storage vendor about the architecture of their enterprise storage. Another concept is the concept of clustered controllers. Such as a clustered ESX environment, we could have multiple nodes in that cluster. And it would give us a greater level of redundancy, also a greater level of performance. Active-active versus active-passive controllers. So looking at the mid-range environment, with 2 controllers, in this example we're seeing controller 1 and controller 2, an active-active would have both data paths being able to achieve data flow. Active-passive, you would have one path, one controller active, and the other passive, in standby mode, waiting in case it's needed for a controller failure. In addition, there's the concept of symmetric versus asymmetric controllers. We may use the VMware native path policies or additional vendor-provided storage, such as Itachi Dynamic Link Manager or other pieces of software provided by your storage vendor. With symmetric, on the lower left, we see that both paths are preferred. There's no penalty for an I/O going to controller 1 or controller 2. We'll get equal throughput and equal response time, equal number of IOPS by going to either controller. With an asymmetrical logical unit access, called a LUA, you would have a preferred path and a non-preferred path. Where both can have active I/O on it, the non-preferred path would have a performance penalty. Either less throughput, less number of I/Os per second, or a slower response time. So in these cases, ESX, which is a LUA aware, there would be a preferred path and a non-preferred path. The non-preferred path would only be used if an I/O could not be completed on the preferred path. Now let's talk about replication from a storage viewpoint. In-system replication is replication within the same storage system. The purpose for this replication is for backup, test and dev, perhaps making a safe copy. The typical technologies used are a full clone, where we take the source LUN and we make an exact copy of that source LUN, or a space efficient, a snapshot, where we only commit the changes to the target, and the source LUN would remain unchanged. Or we can use a combination of both. You may have one full copy and one space efficient copy for different purposes. The advantage of the full copy, the full clone, is that there's no performance degradation to the source while you're performing an operation on the target, such as maybe running a backup or running a batch process in the test and dev environment. The disadvantage is that it requires all the storage space. So if you have a 100 gigabyte data store as a source, you would need a 100 gigabyte data store as a target. Space efficient, if you're performing heavy I/O on the target, you could affect the performance of the source and therefore the application. However, you would only need to store the changes that happen during the period of time you're using the snapshot. If we go to remote replication, which is typically used for disaster recovery, it comes in two basic types: a synchronous remote copy or an asynchronous remote copy. A synchronous remote copy, before we tell the host that the write is complete, we make sure we write to both the source and the target. So there's no difference between the data actually written on the disks at the source or the target. With asynchronous, we would write to the source and then have a write complete back to the host. And at some later time, either milliseconds later, seconds, minutes, we would write that copy out to the target and then say the copy is complete. In these cases, there may be some difference between the data on the source and the data on the target. However, there's no performance degradation if we're going a very long distance from the source to the target. These are typically used for long-distance remote replication. So if you're replicating from, say, New York to California, we would use asynchronous. Whereas if we were replicating from New York to New Jersey, we may use synchronous. So let's talk a little bit about the solutions that Hitachi Data Systems provides. Hitachi Data Systems is a complete provider for vSphere. We're a technology alliance partner with VMware. We've been in active engagement with VMware since 2002. And we provide all the services for storage in a vSphere environment. From disaster recovery to data protection, dynamic provisioning and tiering, so sub-LUN level tiering, thin provisioning, all VMware integrations, VMware and storage administration management, and storage virtualization. The Hitachi Data Systems portfolio, on the high end, we have the Universal Storage Platform and the Virtual Storage Platform. These are very large enterprise storage devices that scale up into the petabytes. The Virtual Storage Platform internally scales up to 2,048 disks and then can virtualize other storage behind the storage platform and scale up to multiple petabytes. On the mid-range, we have the Hitachi Unified Storage. Unified in that it provides both block, either through Fibre Channel or iSCSI, and file through NFS. It comes in three sizes: the HUS 110, 130, and 150, and can scale up to multiple terabytes of data within the HUS platform. Hitachi also provides file services such as High Performance NAS, Data Discovery Suite, Data Ingester, and Content Archive Platform. On Hitachi subsystems, all of our current Hitachi subsystems are symmetric active-active controllers. There's no penalty for going down another path. So they are not a Lua, they're full active-active controllers. So from the HUS through the USPV, through the VSP, and our previous mid-range platform, the AMS, they are all fully active-active controllers. Because of this, we can use the native VMware round-robin algorithm and provide very good throughput with very little administration. Simply turn on the round-robin algorithm and leave it. In addition, the controllers are self-tuning. So if a microprocessor on controller 0 becomes overloaded, it will offload some of its processes to controller 1. They're highly available in that there's no downtime required for any maintenance activities. With storage virtualization, we have the ability with our virtual storage platform or universal storage platform to connect in other storage systems. We can connect up to 255 petabytes of additional storage. And when those storage systems are virtualized, it extends all the features of the Itachi storage, such as the hardware acceleration through the VAAI, or the management suite through the vSphere management plugin. So by connecting into the VSP additional storage systems, and we have over 150 storage systems certified for use behind the VSP, you have centralized management, you have increased availability, and you have increased data migration and mobility. We can also provide 100% uptime availability for the virtual storage platform. So we can guarantee 100% data availability. VMware integration and management tools. Itachi is fully integrated with all of the VMware APIs that have been provided to storage vendors. This includes our command suite, integration with vCenter, vCenter plugins such as the Storage Manager, which allows us to administer our storage arrays through vCenter, Command Suite plugin for VMware vCenter that gives us more granularity into our management, Jet Center for VMware for our NAS, VAAI support, VASA support, Dynamic Link Manager for VMware vSphere, and more. We provide Hitachi Dynamic Provisioning, which gives us capabilities of both thin provisioning and wide striping of our data. So if we put all of our disks into a dynamic provisioned pool, all of the LUNs and data stores associated with it become thin provisioned, but we also stripe the data across all of those individual disks. So instead of having the behavior where one RAID group may be overloaded, not being able to supply the IOPS required, and another RAID group fully use the capacity but not using the IOs required, we can balance that out across all of the disks and get the IOs required and utilize the capacity. We also have the ability of tiering at a sub-block level. So we can put 3 tiers into a single dynamic tiering pool. The storage subsystem will evaluate the frequency of access and migrate that data into the tier that will best suited for those blocks. On a virtual storage platform, these blocks are 42 megabytes in size. And by moving 42 megabytes in size, we may have a particular application which has 20% of its data in Tier 0, 30% of its data in Tier 1, and the remaining 50% in Tier 2. The application does not see any of this tiering. It simply sees better performance and better utilization of the storage. We also support vSphere API for data protection, VADP. It gives us the ability to quiesce the VM, take a snapshot of that VM, and that snapshot can either be a VMware snapshot or it can be a storage-based snapshot using the in-system replication. It can then mount to a proxy server and back that up. Using the change block tracking, we're able to do this incrementally. The iData agent, IDA, interacts with vCenter. It can do auto discovery of new VMs and add them to backup sets. And it can interact with vCenter and tell the VM to either suspend or quiesce using VSS for a backup cycle. The Itachi Data Protection Suite supports VADP with or without the shadow image or copy on write in system replication. With remote replication, we support both true copy synchronous replication and asynchronous replication using Universal Replicator. Both are supported with Vmware on Site Recovery Manager, and true copy is supported on VMware with a vSphere Metro cluster. Universal Replicator is a journal-based replication. So when a write comes into the primary volume, that write also gets committed to a journal volume. The secondary system will then look at that journal and copy any data in the journal over to its own journal and apply it to the secondary volume. So if there is a network outage or a lack of bandwidth in our wide area network, the data will be journaled and be applied after that network bottleneck is removed. In system replications, we have two types of in-system replication. The shadow image is the full clone. It can create up to 9 copies within the same subsystem. A copy on write is a space-efficient snapshot, and it can provide up to 128 generations of the same dataset. We have full Site Recovery Manager support, starting with vSphere 3.5 all the way up through vSphere 5.0. We support failover, test failover non-disruptively using shadow image or copy on write, reprotect, and personality swap. With VMware Metro Cluster, we have full support using Hitachi High Availability Manager software. And the ESX host thinks it sees a single LUN. However, the actual configuration, the ESX host through the HDLM software, sees both the primary and secondary volumes and is able to negotiate which volume is the current active volume set, or the current read-write set. If there was a problem with a volume, such as a data center outage or a power loss, it will non-disruptively switch to the secondary volume, and there'll be no data loss, no interruption of service. For more on our Hitachi Data System solutions, go to hds.com/solutions, and you'll see reference architectures for Hitachi storage and blade servers on VMware. Thank you.